question was for the assignments due on Thursday, you get 3 attempts. It takes the highest overall score that you get. So if you do it once and get 10, do it twice and get 15, and do it last time and do 100 and get 100, it'll take 100. But it'll take that single score. It's kind of cool. A bunch of youngsters making a balloon. Of course, it's kind of in the flight path. As you take off north out of San Francisco International, you go right across the east side of the city on the bay. So I'm not sure how that quite works out. Like a flight path. Actually, that's pretty much the path of the San Andreas Fault, as it turns out. So, 90,000 feet. So planes are, I guess it's above the flight path now, right? For sure. Planes would go up to 36,000, something like that. 10 kilometers. So, you know, the relevance of this is kind of obvious, right? We've talked so far about fluid properties at a point: density, viscosity, surface tension. Now, today, or starting on Monday, we're starting putting it together and looking at behavior when you add all those points together. And so we know that air is compressible, and so as you go higher up in the atmosphere, it becomes less dense because you have less molecules of air above you as you go progressively further out. And when you get into space, of course, it's a vacuum, zero absolute pressure. And so we know that pressure in a balloon stays constant, but will expand the balloon to keep the ratio of pressure to density the same as you go up. And so in doing that, it flexes the balloon until it gets too big, and then it bursts. It's just the same as overinflating a balloon by blowing too much pressure in it. Here, the lack of pressure outside is the atmosphere, which is changing as you go up. And so it shatters, it comes down on a parachute. They must have GPS attached to it. They go looking for it. And then they retrieve it. And so, yeah, pretty clever. The exuberance of youth. Yeah, fun. So, anyway, so I guess we're still too early, but that's fine. I don't really have much else. Any questions, I guess, before we get going? Don't forget, following Thursday, your first assignment's due. Highest score of 3 attempts at it. I think it's the same for all of them. So it covers the stuff up till last Friday, just the material properties stuff. All right. Yeah.
So do we have to submit a written homework or just a multiple choice one?
It's all on Canvas. It's their multiple choice questions. You don't have to submit your working. Is that what you asked? Yeah. No, you don't. Thanks for asking. Okay. Any others? All right. Well, why don't I was going to do this? So I guess a couple of things. TA hours are set now. They're set, so they're Monday, Tuesday, Wednesday, and Thursday. The days before everything's due, not Fridays. And so it's in 111 Hostler. It's down on the ground floor just as you go into the building. So please make use of Isabella on those hours. Junpeng and Matt, if you need it outside, can arrange a time with you. I had a couple of people swing by me on last week. Fine as well. But anyway, use the resources that are available to you. Take control of your education. I don't know whether I'm a good instructor or a bad instructor, but that doesn't go on your transcript if you don't get the concepts of the course, right? No employer cares whether I'm an idiot or not. So just take care of your own, take control, ownership of your own education. So that's that. I will again make the point that just because I say you don't need to get the text, I still think it's a good idea for you to get the text. You know, our sessions are quite concise, and so sometimes if you need the context for that, maybe it's useful to have a book, not necessarily the current edition, but a edition of the book to be able to do that. The videos are all posted, as you can see. The 3 from last week are all online. Hopefully you've looked at the stuff from last week. I thought I would just go through it really quickly, just because I can. I'll put off the volume. So and I apologize if you've already gone through this, but we'll just rip through this. So now we're interested in talking about the behavior of fluids, not at a point, as density, mass, or viscosity, but as they extend in some lateral extent. And so our primary one is to look at as we go into the atmosphere, for instance. And so the relevance of this is climbing up Everest. Why does the air get thin? This is the Mallory step, I think. I'm not sure what this is. Yeah, this is this. This is water as you accelerate in a bus. This is water that's trapped between the double glazing. As you accelerate, why does it get an angle to it? And so we want to be able to quantify what causes that angle. And so to do that, what we do, okay, that's just playing in the background. So I'm just going to do this. So what we might want to do, I'm just going to try running through this. You know, it's easier for us to think about fluids and how the pressure in a fluid changes as you go up by just taking a bucket, a pail of paint, bucket of water, a weightless bucket. We know the mass that's in the bucket, we know the cross-sectional area of the bottom, and we know the weight of the bucket if we know the height. And so if we know those pieces of information, we can calculate what the pressure would be uniformly along the base of that bucket to hold it up. We can take a second bucket and add it to the top of it, and the pressures of that should therefore be additive. And if we know the weight of the first bucket, we know the weight of the second bucket, we can sum them up to get the weight acting at the base, divide that by weight, which is a force in newtons by the cross-sectional area, and that would give us a pressure. And so we'd find that if we do that, that we can rationalize exactly how that would increase in pressure with depth as we go down here. So that's exactly what differential analysis is. And so what we could do is, instead of using a bucket, we could divide it up into lots of little poker chips, and those would be our differential elements. And so the other way of looking at this is the dreaded differential analysis, which I'll go through here. I'll get the derivations, and then we'll just quote these derivations. Is that if instead of a round bucket, we take a differential cube, which is dx by dy by dz. We work in what's called a right-hand coordinate system. This is my right hand, x, y, z. In our class, z is always vertically upwards, increases with elevation, just for the sign convention we use. And so what we can do is we can take this bucket, that's now a cube, and look at the forces that are applied to it. We have the weight of the fluid in the weightless bucket, which is just the area times the height times unit weight of fluid. We could apply a vertical acceleration to it by pushing it up in the vertical direction, or in the x direction, or in the y direction. So that's what this is. And we can look at how pressure changes from underneath the cube to a small change in pressure dP. And if we multiply this by dz dz, we have a change in pressure with z. Doesn't matter. It's explained to you if you look at the movie. So what we can do with that is we can now get a little bit more sophisticated in the expressions that we get, which are here. We end up with 3 differential equations, and we do that by resolving first in the z direction. The first one is in the z direction, then in the x direction, and then in the y direction. Just F equals ma. And if you look at this, this line that's being drawn down here is to separate the part which is mass times acceleration, density times acceleration, from the part that are the forces which are part of Newton's second law, F equals ma. And so it looks complicated because it's a differential, but they're expressions that we get. And so in the first part of the class, we'll use those, but what we'll do is we'll first take these acceleration terms and throw them away. Don't care about them. And in which case, we're left with slightly simplified equations. And the simplified equations, if we throw this term away and look at the equations, we end up with these expressions here. One is that the rate of change in pressure with depth is equal to minus the unit weight. Unit weight is density times gravity. That's true whether we have a liquid or a gas. Important to know that. It's just that the unit weight will change in a gas with pressure, and we have to know that. And from the other 2 equations, we get that the pressure change in the x direction and the pressure change in the y direction are 0. And so we've kind of used that one already. So the drawing to the left is our capillary tube. Remember, from the capillary tube, we said we can cut it off at the bottom, we can lift it up, we can hold the cylinder of water up by surface tension, and we can do that because we know that it's atmospheric pressure under here. So if we can move from atmospheric pressure here to get to that point which is on the same point, so if x is in the horizontal direction, the change in pressure as you go in the x direction doesn't change. So if you're on the same level, by definition, you have to be at the same pressure. So we've used it already. I'm not sure that we've used this already, but we'll use that today. And I guess the other thing that we know is that pressure at a point acts the same in all directions. Pressure in the x direction, pressure in the y direction, and pressure in the z direction are all the same in a static fluid. What a nice looking guy there. Tell you, just so out of the corner of my eye. So, fine. So, if you've also looked at it, perhaps we'll do it today. The two other things we can do is that this is a function of density times gravity. We know that for a compressible fluid, gas, air around us, we know that density changes as a function of pressure. And if pressure's in this term, then we have pressure on both sides of the equation. So things get a bit more complicated. And it turns out that it's not such a simple expression to solve. If we're in water, in a swimming pool, then this is all that derivation. You should have seen it. Don't worry about it. But let's have a look at this. So, if we look at exactly what that should look like, then let's see if I can do this. Right. So, we talked about absolute pressure and absolute temperature. Absolute pressure is that we sit here at 100,000 newtons per meter squared. It's the pressure of the air above us, the column that goes up into the troposphere, stratosphere, whatever. Actually, you could, if you wanted to, from that pressure and the ideal gas law, count exactly how many air molecules there are in the world if you wanted to do that. It's a pretty simple calculation to make. But if we look at sea level, so this is elevation, this is the z direction here, this is below sea level here. And if we plot what the pressure of a gas is, it starts off at 100,000 pascals, newtons per meter squared. And as you go up, this is 100 kilometers, 200 kilometers. So this would be 10 kilometers. As you go up, the pressure asymptotes to zero absolute pressure. Because by here, you're running out of air molecules. There's no a surcharge of air molecules on top of us, and so we feel the pressure is zero. Gravity pulling the air molecules down, which have density, gives us zero pressure. It asymptotes to 100,000 pascals here. If we were to assume that the density of air was constant, at sea level it's about 1.2 kilograms cubic meter, say 1 kilogram a cubic meter, and we looked at how it would change if it was incompressible. That's the red line. It would go up like this. It would be linear. And so as we go down, and clearly that would give us a bad estimation. Obviously on the left side of this curve it doesn't exist, but it would stop at this curve. So that's not very useful to us. If we look at what water would be, sorry.
You correct the formula and then it was a straight line and the x.
So I'm not sure your question.
Like that.
Okay. This is this is actually I'm not sure what that. This line is essentially zero density changing depth, but I think I want to show something else. So I guess I made it big tonight, so I guess I need to make it smaller. Do I do it? Let me draw this. Okay, let's not use that anymore, but let me use this. So if you were to take this, perhaps I'll draw it out on a real piece of paper later, but so this is sea level right here. And as you go up, it asymptotes to zero absolute pressure. So this term here is zero absolute pressure. This is 100,000. If you looked at the change as you go into water and you went under the sea level here, then this is an incompressible fluid, and again the pressure changes with depth, but it doesn't curve because it's constant density as you go further down. If we drew this to scale, this pressure would essentially be much more shallow, right? As you go down a small increment in depth, the pressure goes up a big amount. And that's because the gradient of this is given by the unit weight. So dP dz is equal to minus gamma w over 1. So that's what that means, is that these triangles have to be similar to each other if we write it that way. And so we know that the density of air, 1 kilogram a cubic meter roughly, is 1,000th of that of water. And so this gradient will be 1,000 times shallower. So you go down 1 meter, it will go up 10 kilonewtons. If you want to go 10 meters, I guess it will go 100 kilonewtons. And if you go down 1,000 meters only, so if you go down 1 kilometer, it will be at exactly the same pressure magnitude as this. So this magnitude here, if I could draw a line, would be achieved at 1 kilometer. This, as we saw, was something like 10 kilometers to get to this. So that's the difference. So anyway, that's what you would have seen if you did. Hopefully you looked at the stuff at the weekend. So that's our task for today. And so I will start off from this. I'm not sure if I answered your question, but hold on. So, because I'm not sure. So these are the same expressions that we had last that I noted. These are the same equations that we wrote out, and as I mentioned, the only two expressions that are important are that the pressure as you go horizontally stays the same in a static fluid, and as you go vertically in a static fluid, the pressure changes according to the density times gravity, which is this term here. Density of the fluid as you go through it. What you can do, and I won't do it here, but what you could do is you could take this expression and you could write it as dP is equal to minus unit weight dz. you could integrate between Z1 and Z2 and P2 and P1. And if you did that, you'd end up finding that if you plot pressure versus depth, so this is positive Z, this is negative Z, then we end up with something that looks like this for an incompressible fluid. And it's exactly this expression here. And what it is that this is equal to P1, this is equal to P2, this is equal to Z, which is negative. And we can also replace that, just because it's going to be easier for you to think about this, by some depth below the surface h. So the pressure at a point is equal to the zero pressure. It might not be zero. It could be, if you're working in absolute pressure, it could be 100,000 kilopascals, 100,000 pascals, and adding the unit weight multiplied by the change in height. So this integration is with z in the upwards direction. Again, you have to look at 2-1 to figure this out. So if this doesn't make sense to you, go back to that. But typically, for all the stuff that you'll do in this class, you'll probably use a height, which is just the height of water, to get the magnitude at the lower magnitude. If you want to solve this expression for a compressible fluid, you'll note that this term here is equal to rho g. And so since this includes density, which is a function of pressure, then we have to move this rho term onto the left-hand side. And so if we're integrating this expression here for a compressible fluid, we have to introduce the fact that it's not just g times rho, but rho we can replace by the ideal gas law, right? Oops. So P is equal to rho RT. So rho is equal to P over RT. And if we want to, then we can substitute for this density here in this expression here, which is this, and then integrate. It just gets complicated. So I won't go through that again because it was done in 2-1, and you can look at that. That's why that material is provided. But to summarize, what you should take away from 2-1 is that if you have an incompressible fluid, you can always get the pressure by just looking at the depth and how the depth changes. The pressure will change linearly with depth, and you can get it from an expression like this. If it's a compressible fluid, you get a more complex relationship, which we quoted in 2-1, but we won't deal with here. And that you can then use these two things that you know, this to give you how pressure changes with depth, and the fact that pressure, as you go horizontally, doesn't change at all. And so what we can use those to is use those to make measurements of pressure, which we'll spend most of today doing. So we'll talk about manometry today, and that's all we'll spend our time doing. So these are notes in here, blah de blah. So yeah, we did this last time. I'm not going to go through that. So how are we going to use this? So I will do this. I will go here. I guess this is what I wanted. Let's listen to this.
We're going to make a barometer. So what I have here is a glass tube that's about 800 millimeters long. And I've filled it with mercury almost to the top. And I'm going to finish filling it so that I get filled all the way to the very top. And then I'm going to put my finger over the end, and I'm going to invert it into the mercury. I'm going to set it here and use our
Little beads of mercury
clamp
floating
to hold
around.
it. Now, what's keeping this mercury?
Did you get to use mercury in
hot
high
so
school these
hot?
days?
It's that atmospheric pressure
Too nasty.
pushing down on the mercury, pushing this up. And let's see how tall our column is. 744 millimeters. It doesn't matter what size the diameter of our tube is, as long as it's relatively small. You can see this one's really small. I have another one, it's almost twice the diameter of this one. You can see that the
Doesn't make much difference.
level is the same in both tubes. What we're going to do is compare this crooked
Oh yeah, fine.
barometer to the barometer that we already have.
Same.
And notice it rises to the same level.
Yeah, okay. That's quite useful to us. So we're going to try to measure some pressures. And so I don't know whether it's best to look at these notes, or I can explain it better myself, hopefully. So a barometer is quite useful for us in messing around with this, because it kind of accommodates all the rules of manometry, which I've written out here. And so the manometer rules are these 5 rules, I suppose, and barometer kind of encapsulates them. And so if you go up in a fluid, the pressure decreases, so you can subtract off the pressure. So pressure is equal to unit weight of fluid multiplied by H plus P0. And so perhaps we can draw it slightly differently. So this is, if this is H and this is P, and if this is P0, then the pressure at this point here is going to be P. P1? I don't know, just P. So that's all we're saying. So if you start off at a pressure which is different, then all you're doing is you're taking y equals mx plus c, right? It's just the gradient of a line that has initial intercept if you roll this on its side. And so this is y equals mx plus c, constant, nothing more than that. And so in this, if you go down, and we talked about the sign convention for c, but let's not worry about that here. If you go down, then this magnitude is positive, and then pressure increases. If you're starting off here at this pressure and you go up, then H would be going up, and this would be negative. So manometer rules matter where you go in the fluid. Go down the fluid, you know your ear is going to pop in the swimming pool, and pressures go up. The opposite is true. So those are the first 2 things for us to be aware of. If we go horizontally in a fluid, then the pressure doesn't change. If you have one of those fancy swimming pools in a hotel, indoor, outdoors, it has a wall between them, and you're some depth on the inside, you swim under the wall and are at the same depth on the outside part of the pool, then the pressures would be the same, just as we've seen for capillary behavior. If the tube is evacuated, so it has a pressure in it, then the pressure has to be the vapor pressure. So if it's water, the water will boil and become vapor over water. In the barometer is turned upside down, filled with mercury, thumb over the top, might want to wear a glove, turned upside down and put in a dish. The weight of the mercury in the top of the bulb of the tube, there wasn't any space there before, but the weight of it causes the mercury to boil. It cavitates, and so it becomes mercury vapor only. There's no air in there. And so that mercury vapor has a specific pressure attached to it, which we can define, and therefore that is a characteristic of it. So if it's evacuated, it's the vapor pressure. And finally, if it is a gas, then we know that the density of water equals times 1,000 the density of air. And so if we multiply both of those by G, then we know that the unit weight of water is about equal to 1,000 times the density of the gas, air, I guess. And so if we're going up in a gas, it probably doesn't matter very much how far we go up, because the pressure doesn't change very much compared to the water or the liquid that's in the system. And so when we use manometry, as we saw for the barometer, we use a liquid to measure behavior. So we can measure pressures in liquids and gases, but the gauge fluid always has to be a liquid. So let's look at the barometer in detail. Barometer is kind of cool because it encapsulates all of these laws. So don't know if I can draw a good barometer or not. Probably doesn't, it could be water, I suppose, right? Didn't change. And so it's worthwhile talking about these things. What happened was we got a meniscus. We have a height rise. And we have pressure atmospheric. And so what we'd like to do is be able to figure out exactly what this atmospheric pressure is. We don't know what it is. So we'd like to be able to figure it out. If we know that the pressure in here is the vapor pressure, it's also almost equal to 0, but doesn't matter what it is. So what we can use is we can use the manometry equation to go from this point here through the system. So what do we know about the pressure at this point here? We know that these are simply connected and they're on the same level. And so we know that from this, by definition, the pressure here has to be the pressure A. And so we could write an equation for this by saying that the pressure A here is the same as here. We're going up, so we're subtracting off the height multiplied by the unit weight of mercury. And that's equal to the vapor pressure of mercury. So the density of mercury, I've got it written down here, is 13,600 compared to 1,000 kilograms per cubic meter for water. And so and also the vapor pressure of water is equal to 0.025. Whoops. Atmospheres. And an atmosphere is the same as a bar, as in barometer. This is a barometer, obviously. And 1 bar is equal to 100,000 pascals, newtons per meter squared. Right? So it's tiny compared to this magnitude. And so we could, let's make this 0, just because we can. And then we know that the atmospheric pressure is equal to H times density, hg times gravity. And so from that, the height should be equal to atmospheric pressure times density of mercury times gravity. And so what's that? It's 10 to the 5 newtons per meter squared divided by, so 1, 2, 3, 4. So 0.13 times 10 to the 5 kilograms per meter cubed times 9.81. I'm going to write 10 meters per second squared. So these cancel out. These cancel out. This should be equal to 0.13 into 10 is, I'm guessing it's 0.75 or 7.5. No, 0.13, yeah, is 7.5 times 1 over 10 equals 0.75 meters. So you saw that in the our movie with Miss Brainbox, that the height was something like 744 millimeters, right? So that's the same. This is 750 millimeters just by doing this rough approximation. And so the key here is that we've used all of these components of the so-called manometer rules. We've gone horizontally on a pathway that's simply connected. In other words, we can get from this point to this point that's on the same level without going through a wall. So this pressure here has to be the same. We've gone up, so we've subtracted the height of gravity, the height of the column from the pressure, and multiplied it by the unit weight. We've ended up in an evacuated space, so this evacuated space is equal to the vapor pressure. We've chosen to make it equal to 0, even though it's a very small number. You can do it with a small number and figure out what it is. And so we've used that to calculate what h is. The reality is that's kind of a circular argument. Why do you want to do that? Well, what we want to do is we'd like to know what the atmospheric pressure is. And so what we'd do is we'd measure the height. We'd know what the vapor pressure of mercury is, essentially 0. And from that height, we'd be able to measure what the atmospheric pressure is. And so you'd be able to use that to gauge small variations in atmospheric pressure, which is the highs and the lows of the atmosphere as weather moves in. So that's what a barometer is used for, obviously. You could also use water in this. Some of these barometers are filled with water. I guess if you used water, if water is, the density of water is 1,000 kilograms per meter cubed. The vapor pressure of water, I wrote down, is 0.03 atmospheres. As opposed to 0. Oh, there's an extra 0 in there. Mercury, the vapor pressure is really low. So the vapor pressure for water of H2O is actually very small also, so you can do this. But just from this, if we used water, how tall would the column be relative to that? How tall would the column be to measure 1 atmosphere? (13 times 0.75, right? So that's about 10 meters. So H for water would be about 10 meters. 10 meters is 3 stories. 1 story is 3 meters or 10 feet, so it's 30 feet. It's the height of a house. So if you want to measure it with a barometer in your living room using water, that's kind of, you'd have to put it up your chimney, I guess, to do it. But because you can do it in with mercury, mercury is dense and also has a super low vapor pressure. For water, we also know what the vapor pressure is, so we can calculate this absolutely and do that. Okay. So that's really what we want to be able to do. Okay. So that is a useful example because it encapsulates all the principles of this. I guess the other example would be the thing we didn't use was that if you go up in a gas, the pressure doesn't change very much because the unit weight is equal to 1,000th of the unit weight of a liquid like water. I guess it would be 13,000ths the unit weight of a liquid like mercury. And so if you wanted to look at the pressure in this, then the pressure at the top of this, I'm not going to draw a point there, the pressure at the top of this is going to be equal to the pressure at the bottom of this because the unit weight of this vapor is essentially zero density. So the pressure in that bulb is essentially, there's no change as you go up in elevation. Okay? So, know these manometer rules because we'll use them. Let's do some examples. So I won't go through this, blah, blah, blah. We've gone through this. This is the example. If you want to be able to check it out, you can check out all the things that I've said, hopefully here. And it comes in with this. This is in inches. Yeah. So, manometry. Environmental systems engineers, you want to look at groundwater flow. You want to measure the pressures in a well because you want to be able to measure a pressure in the well here and a pressure in the well here. If they're different, then it drives flow from A to B. Just like in a petroleum reservoir, if you have two different pressures at two different locations, that's what you do. You draw down the fluid pressure to suck out the oil or gas in a reservoir. We can do exactly the same thing here. So what we'd like to do is we'd like to calculate the pressure in our well. So the best thing to do is to work from the point where you know the pressure and write it out. And so here I would write, if I wanted to know what PA is, I would write out P0 plus H1 gamma water equals PA. If I was working in gauge pressure, the gauge pressure I feel here is 0 kilonewtons, newtons per meter squared, or 100 kPa if it's absolute. If it's in gauge pressure, let's do both. Then this would be 0 plus H times unit weight of water equals PA in gauge. If I want it in absolute pressure, then this would be 100 kPa plus H times gamma W equals PA in absolute. So they differ by 100 kilopascals. That's all. That's all that gauge means. Both are correct. It's just the reference by which we're calculating them. If we're wanting to do something fancy with the ideal gas law, we'd probably want it in absolute. But for almost all the applications in this class, we'd probably work in gauge pressure, where a gauge, a Bourdon gauge that you measure pressure in here in this room would say 0 psi, 0 kPa. Just like when you pump up your tires, it uses gauge pressure, hence the term gauge, right? Okay. So all we'll do is we'll do some examples. So manometers are also used to measure pressures in pipes. So this isn't a chemistry flask, it's a pipe going into the page. And we might want to know what the pressure is at this location here. So again, we'd start off at a place where we know the pressure, and we'd end up at the pressure we'd want to calculate. You could do it by using the formalism here, but let's just do it differently. So let's use this. So I'll write it out. P4 is this. We want to get to P3. To get to P3, we have to add H2 times the unit weight of the gauge fluid, not a gas, gauge fluid. Here, if we're in this fluid, we can get through this pipe to get to this point here, which is exactly the same level. So this is to get to P3. Now we're at P2. So to get to this point here, we have to subtract H2 times the unit weight of 1. And that is equal to the pressure at point A. So if we're working gauge pressures, which we almost always will be, then by definition, this is 0, atmospheric. This is a height which we know multiplied by the unit weight of this fluid. If it's mercury, it's 13,000 kilograms per cubic meter times acceleration due to gravity. If it's water, it's 1,000 kilograms per cubic meter. So let's assume it's water. In this case, if it's water, this unit weight would be 1,000 kilograms per meter cubed times 9.81 meters a second squared, which is the same as unit weight, which is 9.81 kilonewtons times 10 to the 3 newtons per meter squared, if you're unsure of the units. And then if this was if this was a gas, we could throw away this term because it's a thousandth of that, and we could calculate what the pressure is. So if you're unsure about it, go through the working, you end up with exactly the same result. And so the other result is, I guess, if the unit weight 1 is equal to a gas, then this would be essentially equal to 0. And then, as a result of this, the pressure in the flask would equal to H2 gamma gauge. Whoops. And so you can't always assume this, but if this is a gas and this is a gas, the difference in these elevations is just the difference in pressures between that on the outside and that on the inside. In this case, this pressure is higher than this pressure, right? Because you can imagine inflating the balloon, it pushes a pressure to push against this. So you're actually, by the pressure that you're applying here, you're holding up this column of fluid which is trying to collapse down onto you by its separate weight. And so in this case, the pressure in here would be higher than out here. If it was the other way around, then the pressure outside would be higher than the pressure inside. So, okay. And this is this. So if there's a gas in here and we don't care about the unit weight of this, then the equation we had reduces so that the interior pressure is just the the height of the mercury column, or the liquid column, multiplied by its density. And again, we like to use a dense liquid because we don't have to have such a high column to measure difference. So these are the manometer rules. Subtract when you go up, add when you go down. Use 0 for gauge pressure. If it's a closed vessel, use the vapor pressure. If you have specific gravities, it doesn't matter. Okay. Do we want to do more, or I don't know? I can't remember what the different ones we have are. I'm just looking at these. They're pretty much same old, same old. So here again, you want to work. This is done the wrong way around, I think. The easiest way to do this is to work from something you know and get towards something you don't know. But this is written the other way. It's written from something you don't know to something you know. But you can do it either way. So you can start off at PA. You go up 10 meters in whatever the unit weight of the fluid above PA is to get to this point. You go down 5 plus 5 meters in the fluid next to it. They cancel out, so you could just have gone directly over here, right? Because you can we're on the same level. We go down 2 more meters in this same fluid to get to here. We can go across to this point here, and then we go up 2 meters in this fluid, the red fluid, plus is that right? No. Right. Oh no, that's right. Fine. Yes. I see what I've done. That is right. We've gone down in water 2 meters, which is this term here. And then we've gone up in mercury, which is 2 meters plus 5 meters, 7 meters. And that gets us to this point, which is equal to atmospheric pressure. So if we'd written it the other way around, starting here and going through to end up at this, we'd have this immediately. But we just have to do the substitution for these to get the magnitude of this particular pressure here. And it's given here. And you can go through the numbers if you so wish. This is the density of mercury, 133 kilonewtons per meter cubed. So this is 133 kilonewtons per meter cubed. And you have to be consistent with your units as we talked earlier, right? Okay? Yeah.
Can you review what the V and the E stand for in the Manometry rule?
Oh, negative and positive.
Like,
Plus VE is positive.
what is the V?
I'm just, it's my shorthand. If you write the word positive, you're not the first person to have asked this question, is equal to shorthand. It means positive. Thank you. Good question. What language is this guy speaking? And writing? Badly. Okay. Any other questions? Joe? I mean, it's all very logical. It's almost formulaic in terms of doing this. Differential manometry. Let's so we can do this. So again, if you write this out, we can work. So this could be a liquid, and a gas. Doesn't matter. We'll treat them all as the same components. So let's write the manometer rules for this. So let's work from PA, as I've done here, I guess it's written out, to go through here. PA, here. We go to this point. That's the same pressure. We go down in fluid 1 to get to this point here, plus H1 gamma 1 gets us to here. We go across the same fluid to get to this point here. We're still at the same pressure. We go up to get to this point. So we subtract off H2 times unit weight 2, because we're going up this. This is the gauge fluid, the fluid that is the mercury. And then that gives us the pressure at this point, and then we go up again to get to 0.5, and that would be minus, because we're going up, times H3 times the unit weight 3, and we arrive at our destination. And so what we could do, this is the same expression that we have here, so we could subtract PA from both sides. If we do that, by definition, we get rid of these two terms because they cancel out. And we have just this expression here. And this is a differential pressure between those two. So this is a differential manometer. The interest in doing this is if this was a gas and this was a gas, then the unit weight of fluid 3 would be about equal to the unit weight of fluid 1, which would be about equal to 0 compared to the gauge fluid. And if that was the case, then this term and this term would drop out. And if we rearrange things, the differential pressure between the two pipes going into the page would be equal to minus H2 gamma 2. These fluids are inconsequential if they're gases. Gauge fluids are liquid, 1,000 times larger, so we can do this. That's the reason why. And we get a very simple expression. Again, it's just the differential height between the mercury in these two limbs. And in this case, again, the pressure in this pipe would be larger than the pressure in this pipe because it's offset. If it were the other way around, it would be the opposite. If we weren't very good at being able to resolve exactly the height difference between this level here and this level here, what we could do is we could cant the tube over so that a small differential change in height manifests itself as a long differential change along the tube. So if we can measure this at higher resolution because it has a bigger range, then that might allow us to get a better reading of the difference between these pressures. That's the point of this one. I'm not going to do it. We're right on the witching hour. And so these are all backed up. And well, maybe I'll talk about those next time.